All right, welcome everybody to week 6, day 1? Yeah, week 6, day 1. Today we're going to be talking about vectors. Vectors are one of the most important concepts in computer science, and they basically answer the question of like, what do you do if you need a lot of variables all at once? So an easy example of like when you would need a vector is if you were to be doing something like tic-tac-toe, right? So if you were trying to code tic-tac-toe, and you didn't know vectors, it would start getting really dicey, right? So what's going on, Cameron? You'd have to do something like this, like char upper left is equal to space, and char upper middle equals space, and char upper right equals space, and char middle left equals space, and char mid equals space. I don't even want to type the rest. I'm bored already. Okay. So anytime I need to make more than maybe like 3 variables at a time, you might find me type int x comma y comma z, something like that, maybe. But anytime you find me trying to make more than about 3 variables at once, I'm going to do something called a vector, because this code gets really, really annoying to work with. Like if you wanted to find out if you had a victory using like 9 different variables like this, you have to do this. Like if upper left double equals x, and upper mid double equals x, and upper right double equals x, then cout x wins. And then, oh man, I don't even know. What do we got here? Did I forget something? I did forget something, didn't I? Cool. And then we could do like middle left, middle right. You know what I mean? Like it just your code's gonna start looking like garbage, right? And that's just for like tic-tac-toe, which is actually, maybe you could probably do it this way, 9 different variables, but it's gonna be absolute and total garbage to do so. So there is a better way, and the better way is by making a vector. And so a vector allows you to make as many variables at once as you want. And even better, it allows you to like loop over those variables. So you can say if any 3 of them are x or whatever, then you win, or something like that. So, although it's not tic-tac-toe, but you know what I mean. So we could do something like this. We could have a vector of chars by the name of vec of size 9. Okay. And this makes 9 variables named vec.at 0, vec.at 1, vec.at 2, vec.at 3, vec.at 4, all the way up to vec.at 8. Okay. It doesn't go up to 9, all right, because we start at 0 in computer science. So it's like the students are like, there's only 9 test cases. I'm like, no, there's 10, because it starts at 0. 0 to 9 is 10, all right? And so if we have 9 spots in tic-tac-toe, right, then the spots are going to be labeled 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so they go from 0 to 8. Let's make dot, like that. Okay, and that is how you access the individual variables. Each of these variables can be read to and written to independently of each other. So I could say, for example, vector.at 0 is equal to x, and I could say vector.at 5 is equal to O. Are you guys with me on this? And I could like cout vector.at 0 and vector.at 5. Does this make sense? What is this going to print to the screen? I got some hot tea for lunch and I left it in the car by accident. So I still have hot tea now. It's one of the benefits of Fresno summers is that if you leave a hot drink in the car, it stays hot. XOXO. Yeah, very good. So yeah, it's going to print X, then O. And is that an O or an O? There we go. Yeah, sorry, it was a 0 actually. Should have been a capital O. My bad. Okay, so yeah, so basically each of these 9 variables you can just read to and write to, but you've got the benefit of doing something like a for loop. So you can say for int 4. For int I equals 0, I is less than vector dot size, I plus plus. If vector dot at I is a x, count plus. Okay, and so what this code will do is the first time through the loop, I is 0. And so it'll say if vector dot at 0 is x, add 1 to the count. Next time through the loop, I is 1. If vector dot at 1 is equal to x, add 1 to the count. Vector dot at 2 is equal to x, add 1 to the count. So what this code here is doing is it's going through the 9 elements of the vector, and it's counting how many x's we have. Okay. And so you might ask, like, what are these initialized to? Vectors initialize their elements to 0. Right. So they default initialize or value initialize. I don't remember the exact precise term for it, but basically, if you have a vector of integers, all of them get initialized to 0. It's not like your regular integers that don't get initialized; they get 0 initialized. Okay, and chars get 0 initialized too, which is the null character. Okay, and so don't have to wait for food to defrost. That's true. Just toss it in your car, and it'll defrost for you. Okay, so for example, if I said vector dot at 0 is equal to x, y 5p, and 2, and 4, and 6, and 8, and maybe I'll make an O up in here somewhere or something. Okay, so then at the end of the day, I'm going to see out the value of count. Okay. So what this is going to do, it's going to count how many x's are in the vector. So I start by setting vector dot at 0, 2, 4, 6, 8. So about half of them, rounded up. 5 of them are going to get set to x's. And then elements 1, 2, and 3 are going to get set to O. Now the other ones are going to be left as null character. Okay. How many x's is it going to find down here? Be careful. I made it slightly tricky. So this is going to go through 0, 1, 2, 3, 4, 5, 6, 7, 8. Count how many x's are in there. Then it's going to print how many there are. Looks like it should be 5, right? 8, and 6, and 4, and 2, and 0, right? Looks like it should be, but somebody made an illegal move in tic-tac-toe. Normally you can't overwrite somebody else's move, right? In fact, the first time I wrote an AI to play tic-tac-toe, I had a bug in it. And wherever you moved, it would just move on top of you. So if you took the center spot, it would replace your thing with it. And then you took the corner, it would replace your thing with it. And I was like, it's actually a really good AI. It's not following the rules. But like, you can't beat it. You know, like, it's impossible to beat. You know, you make enough moves, it's going to win every time. I'm like, you know, it's artificial stupidity, but like, yeah. So right here, this is overriding. So this one is going to. This guy here is going to get overridden here. You guys see that? So all of these things are just individual variables. They're just 9 variables all living together. And variable index 2 has been overridden by an O via this brilliant AI. And as you can see, most of you got 4. Okay. So for all 6 students that are participating in class out of the 16 that are streaming right now, out of the 40 that are in the class. Okay, now, one thing I want to mention here is this warning here. So today in the in-person section, we had a guy by the name of Nick Muya come in. He's Mincarelli's personal hero. Mincarelli kind of looks up to Muya a lot. And so if you look up to Mincarelli and be like, wow, that guy is so friendly and so helpful, I want to be like him someday. You know, it's in part because of the skills of our previous TA from a couple of years ago. He came in, he's working at Microsoft now. And so one of the things he said about working at Microsoft is that they do use using namespace STD. So suck on that. You see your Irvine professors that wrote a 5-page essay on why you shouldn't use it. Microsoft does it, and Microsoft never makes any mistakes when it comes to computer science. And B, Microsoft doesn't allow you to compile with warnings. So if you have any warnings in your code, it's reject. The only warning he said they would allow is unused return value, I guess. Microsoft makes all the mistakes, but they have lots of power. Windows 11, yeah. Yeah, I know. I had trouble saying that with a straight face, but okay. So what's going on here is that vector.size returns a 64-bit unsigned int. Okay? And anytime you compare a signed and an unsigned integer, this guy here could be negative, this one here can't be negative, is you can very easily get mistakes. As long as they're both positive, it's probably going to be fine. There's going to be an issue if you ever exceed a vector of size 2 billion. Probably most of your vectors in this class won't be bigger than 2 billion. But if I ever becomes negative, then it won't work the way that you think it will. So the proper thing to do here is to do the proper thing to do is anytime you're comparing I with vector.size, you need to make it a size t. Size t is just an alias for a 64-bit unsigned integer on our system. On a 32-bit system, it would be an unsigned 32-bit number. They make mistakes. They do decide industry standards. Yeah, but like me telling the Irvine professor, like Microsoft does it, like is not probably going to be very convincing, considering how many mistakes Microsoft makes. So, anyhow, but their policy of not allowing warnings is a good one. I don't allow warnings in my own code when I'm coding professionally. Warnings are there for a reason. A lot of students will ignore them because, hey, my code compiled. You know, like let's say I've got a function here that returns a string named I don't know. Somebody give me a function name. I'm out of ideas for names right now. Just some function that's going to return a string. Vecna, beautiful. We're going to call it the head of Vecna, and it's going to take in an integer, and like if x is odd, return. Actually, we'll just call it return head, and if x is over 10, return I. If x is less than 10, return hand, right? So you've got the 3 artifacts of Vecna. You've got the eye of Vecna, that if you pluck out your eye and put the artifact, the eye of Vecna, and then it gives you incredible magical powers. And seeing you cut off your hand and attach the hand of Vecna, you get incredible magic powers also. And if you chop your head off, put the head of Vecna on, you're dead, because that was a practical joke. So it's also in Stranger Things, I think, season 3, right? So okay, so let's write this code. If x modulus 2 is equal to 1, another way we could say this, if x modulus 2, it will return head, move, head. If x is greater than 10, return I. If x is less than 10, return hand. Okay. And so if we were to see out Vecna 21, what should this print to the screen? Oh, every time you saw a vec, you're just like, nah, that's funny. Okay, so what is this going to print to the screen? We pass in 21 here. And is 21 less than 10? I? Head, right? Because 21 is odd. 21 modulus 2 is 1. 1 is true. So it will return head. And when you return, you don't move on to the next lines. So this is going to return head. Okay. So if we compile this, we're going to get a warning because I did this deliberately. Yeah, control reaches end of non-void function. I don't know. Seems fine to me, says the student. If we run it, we get head. Everything's fine. Let's try this again with, I don't know, 30. What is this going to print out? Aye, Captain. All right. Good. Aye, good. And then if I pass in, I don't know, 0 or -10, let's say. What is this going to print? Good. Everyone give a hand emoji to the people that said hand. Very good, very good. So we got a hand. All right. Now, what's that going to print? Eye, head, hand. What's it going to print? Head. What is 10 modulus 2? If 2 divides into 10 5 times, there's a remainder of 0. Is 0 true or false? None? Nothing? So we got a problem here. I got a little problem here. And the problem here is that we have a function that we promise is going to return a string, but we're not returning anything. Okay, let's find out what it does. We get a warning, and this is why I'm saying don't ignore warnings. Like at Microsoft, they turn warnings into errors, right? And that's what happens. It's not printing out nothing. It kills your program. Your program just died. This is actually... Anytime you see a warning, like, you need to pay attention to it. Like, it's valid C++ code. And the reason why it's valid C++ code is because the compiler is not smart enough to always know that your code always returns something or not. Like, it's actually provably impossible for it to know. But it's giving you a warning because it's like, it really looks to me like you're actually not covering all your bases. And so this code is segfaulting. It's actually destroying your program. It's not returning nothing. It's actually crashing your program. And this is a pretty serious problem, right? Like it's generally considered bad practice, even at Microsoft, for your code to crash, all right? So, don't tell me I said that. So yeah, paying attention to warnings is really important. So there is one warning though that I will ignore, and that's the same one that Microsoft ignores. There's maybe 3, but they're all kind of related to each other. So there's a function called system, and system allows you to run a command from the Unix prompt. You will see a lot of people do something like this: rm-rf star or tilde. That deletes everything in your home directory. Don't do it. If you ever see somebody on Discord or like online or something, and you're like, hey, how do I find files? And they tell you, oh, type in rm-rf, so anything. Like, don't listen. Like, they're trying to screw with you, right? Rm is the delete command. Rf means recursive and force. That's your home directory. If you type this in, it will destroy every file in your home directory. Don't do it. So let me show you a nicer one. Figlet. Figlet will banner print things. Like, I love Seaside. Okay? And so system will actually run a Unix command for you. Okay? I'm going to get Vecna here, because I don't like that sitting around. And when we compile it, we're actually going to get a warning that we're ignoring the return code from system. And we can run it. It works fine. I love Seaside. And if we wanted to add colors, we can type the results of this into lolcat, like that. And there we are. Colors. I love Seaside. Pretty cool stuff, right? It's giving us that stupid warning, though, because we're ignoring the return value of system. And this is something that personally irks me. I actually think it's bad design on the standard library's fault, because system has an attribute called no discard, which means that if you call it and you don't do anything with the return value, then it warns. It throws a warning at you. And I feel like that should only be used on functions that are pure functions. In other words, you pass a value to them, you get a value back out, like in math. Like, there's absolutely no point for me to do this, right? Like, if I just call absolute value of 10, like that, this does absolutely nothing. That's what the ab stands for. It does absolutely nothing. And in fact, we are getting a warning here, right? We're ignoring the return value of a function. right? It's like, yo, you're screwing up. Okay, this does nothing. It's going to do a computation and then do absolutely nothing with the result. This is pointless. Likewise, if you compute a square root, without doing something, we might need CMath for that. Like all this kind of stuff. Like, yeah, sure, you should probably throw a warning on it. No warning on square root. Okay, well, I think there should be a warning on this, but this has a warning, and I don't think it should, because the return code from system int return code equal to system if return code error occurred. Like, this is what you're supposed to do, right? It's like if you call Figlet and it doesn't work, like, you're supposed to see that there's an error and then, handle it and stuff like that. If I do this, there's no warning, right? Everything's fine. But here's the thing. Like, a lot of the times when I do this, like, I don't care if it fails. Like, I really don't. And so, like, a lot of times I'll just, like, not care about the return. It's kind of like down here, right? Like, how we could, like, return, like, 10 or return 0 or something. Like, you'll see in everyone's C++ code, return 0 at the end of main, even though you don't need it. Like, you just delete it, and it's exactly the same code. Everyone puts it there because that's the return code. That's the error code that goes back to whoever called us. And that is what is popping out right here. And it's yelling at us for not paying attention to it, despite the fact that, by default, Unix doesn't pay any attention to it. It's just baffling design. So if you want to do that, you can capture the return value like that, and it works fine. This, however, will generate a different warning, and that warning is called you're setting a variable and never using it. And you'll get an unused variable warning, and it's just like, it just really wants you to handle that error. And sometimes I just really don't. And so there's a way of turning that off, which looks like casting it to void and nodding it like that. And there we go, the warning's turned off. If you don't not the value, then it will still give you the warning, which is frustrating because casting it to void is supposed to turn off the warning, and it doesn't. So Mincarelli showed me that trick in class today, and it works really nicely. So yeah, it's just super stupid. So that's a warning that I ignore. I also ignore unused variables and unused parameters. And the reason for that is because, like, when I'm doing development work, like A and B, and I'm like doing some stuff, like, I think I have that warning turned off. Let's see here. That's Clang. Right? Do you see that? So I put in two parameters up here. I'm only using one of them. And so it warns. It's like, hey, you're not using the second parameter. And that's frustrating because sometimes, like, I'll just have a parameter that I just, like, haven't gotten around to implementing yet. Or, like, I have it there for future proofing so that people can pass a variable there for options or something. But maybe I'm just not using them yet. And so it's really annoying getting, like, a warning on that kind of stuff. So I have unused variables turned off by default. If I make a variable here and x is equal to a plus b, okay, now I'm using a and b, so that's going to turn off the warning on b. But now I'm getting a warning for unused variable x, right? And it just looks like, I don't know what to do with it. Why is the name Figlet? It's just the name of the program. So there's a program called Figlet. Juju, right? And it just banner prints things to the screen. So, like that. So it's just a program. I don't know, fig characters. I don't know what it stands for, but okay. It makes testing lines a couple. Yeah, exactly. So, like, that's why I have those warnings turned off, because sometimes, like, I'm doing development and it's like yelling at me, like, you're not using B, you're not using B, and I'm like, chill. I'm getting to it. You know what I mean? Like, I'm getting to it. Like, just shh. You know? Like, and so, yeah, you're absolutely right, Alessandra. Like, it does make doing incremental development annoying. And that's one of the problems that I have with like Microsoft IntelliSense and like other things like that. Like it'll underline things like you have a parameter here and you're not using it. You're not. I'm like just wait, please. Just I'm getting to that part. Just hang on, just chill, please. And Microsoft IntelliSense has zero chill. Like you're typing. It's like, oh no, I don't know what a C out is, and underline. Oh, I know that. Oh, but there's no semicolon. Oh, that's an error. And I'm like, please, just wait for me. Just wait for me to finish, please. Okay, that's fine. Yeah. Honestly, like a lot of the times when doing professional development, I just turn that stuff off because it's more of a distraction to me than, or I mess with the settings so that like like you saw there, like when I was working on this, Commander of Conqueror doesn't like throw any errors until I hit escape, and now it's like, oh, okay, right. And even still, like Commander of Conqueror like annoys me like a fair bit. Okay. All right. So so learning point number 1 for today. 1 is vectors can be used to make lots of variables at once. Learning point number 2, always fix your warnings. Okay. Possible exception, unused parameters, and variables. Like I said, like especially when you're doing development, like maybe later, like when you're ready to like turn everything in, like you want to know, like, oh, you made a variable and you didn't use it. Like, oh, okay, let me delete that. But like in the meantime, like, shush. And then Clang has something. Clang ++ has something called warn on everything, and this is just a thing. Like it actually there's only one error, and that's in my own. That's in readlib. I need to fix that actually. Thank you, Clang. That's actually a good point. I need to fix that. Okay. So anyhow, normally for most projects, everything just produces like 30 pages of warnings that don't really mean anything. Usually, that one was actually good. That was actually a mistake on my part. So, don't use everything. So, warning levels. That turns on all warnings. And so if we have things like an int I here, and we got like uncaught thing there, then all warnings doesn't show any warnings. That's because all warnings are not all warnings. If you want more than all warnings, you have to use extra to get all warnings plus extra warnings. And then you get that. And then if you want more than extra, there's everything. And so wall, W-all, equals quote unquote all warnings circa, like 2000. If you want more than all warnings, and then there is W everything, Clang ++ only. Turn on annoyingly high level warnings. A lot of which you can ignore. Okay, you guys understand? By default, when you hit compile, by default it turns on all extra. It turns it causes errors to kill the compilation, so it doesn't keep going. That deletes a lot of like extra errors as well. Pedantic errors, pedantic It ignores the sign comparison warning that we were seeing there. Turns off unused variable warnings, turn off unused parameter warnings. So those are the 3 warnings that I sort of ignore. And the sign comparison I kind of flip-flop on. Compiles it using C++20. Debugging turned on. The standard library has debugging turned on. It turns on the undefined behavior sanitizer, and it turns on the address sanitizer, both of which are amazing things. Okay. That's, if you ever go to another institution, copy those flags with you, because this thing in particular here, that's not something that Jedi will teach you. Like, I've sent students all over California, and like, apparently very few professors know about address sanitizer and UBSAN, and they're incredible. I don't think anybody should be teaching C++ without knowing about UBSAN and ASAN. Okay, so let's get back to vectors. Okay, so yeah, that'll count how many X's are in the code. Now, if you don't give a size, you can still do this. X, O, X, X, O. Okay. So, how big is vector.size? So if you don't give a size, it'll actually, but you initialize it this way. This is called universal initialization syntax, or braced initialization syntax, or an initializer list. There's a lot of different words I've seen people use for it. It will figure out its size from the right-hand side of the equal sign. So how many elements are on the right-hand side? 6. Yeah. So this is like I declared a vector of size 6 and set the first element to X, the second element to X, the third element to O. And by the third element, is that index? So is this O here? It's the third element, right? 1, 2, 3. It's the third element, but is it index 3 or is it index 2? What do you think? In C++, we start counting from 0, not from 1, right? Yeah, it's index 2. Okay. So if we've got 6 elements here, they're going to range from 0 to 5. All right. So index 0 is this fellow right here. Index 1, index 2, index 3, index 4, index 5. Okay. So we're setting index 3 to be O. And then we're going to count how many X's are in this vector. So tell me, what is it going to print to the screen? We've got XSO, XSO, and then we're setting element 3 to be O. How many X's are we going to have at the end of the day? Is there a song called like X's and O's or something? What's that by? You guys know what I'm talking about? Stable diffusion. Is that the one? Okay. All right. Path of exile. Get back to you later. Peer review. Get back to you later. All right. Liking. All right. Cool. All right. So yeah, we're gonna have 3, right? Because vector.at 3, 0, 1, 2, 3. This X right here is going to change into an O, and then there's going to be 3 X's left. So when we print out the count, do you guys understand? Where have you seen this pattern before? Because this pattern is actually very important. Let me put it back to the proper method here of a size t. Remember, size t is the right way of doing it. Anytime you have size returns something of the type called size t. That's what you want to use there. Where have you seen this pattern before? Where like you're starting at the first element of something, You're going one to the right, one to the right, one to the right, counting how many letters are in it. Yeah. Isn't this a lot like a string? If you want to see something weird, compiles just fine. Three. So you've been using vectors for a while. They're just called strings. So a string is basically a vector of characters with some extra stuff on it for like finding and substringing and stuff like that. Yeah, it is. Yeah, a vector of chars is is a string. Vector chars is actually less powerful than a string. So in this case, I'd probably use a string. Basically the same for this. Okay, so yeah, so starting at the first element, going to the end. So if the first element is an x, yes it is. We add 1 to count. Go to the next element. Is this an x? Yes it is. We add 1 to count. Go to the next element. Is this an x? Nope. Go on to the next. Is this one? It was originally, but we changed it here. So go on to the next element. Is an x? Yes. Go on to the next element. Is an x? No. And we're done. So it'll output 3. Okay. And we don't need to return 0 because we don't like typing things that don't do anything. Okay. So, yep. So one way you can make a vector is like one vector. Let's just say vector of ints named vec1 of size 100 makes 100 ints. All initialize to 0. You make a vector of ints called vector2. Makes 10 ints. Initialize to 1 through 10. And then you can do this. Vector of ints in vector3 semicolon makes 0 ints. Now you might look at the third option there and be like, well, that's not very useful. For the first one, you got 100 variables. You could do like vector1 dot at 6, like there's all sorts of things you can do with it, right? Is equal to 42 and cout vector1 dot at and 30. Right? You got 100 variables to work with. Why on earth would you make one with 0? It kind of seems pointless. Like what if we tried, cout into like vector3 dot at 10? What will this do? What happens if we try using the dot at operator when you're out of bounds? Do you remember what it did for a string? Error? Crash? Out of bounds? So remember, a vector and a string are basically the same thing. So did it make an error? Yeah, it did. And it's a good kind of error too. So if you run your code and you get to that point, then it nicely kills your program. This is actually really nice. It says, hey, you're out of range, you're out of bounds. You tried accessing element 10, which is bigger than the size of the vector, which is 0. You tried accessing an element that's not there, and it kills your program. This is actually really good behavior. And to contrast it, let me show you what happens when you use square brackets. Because you will see a lot of people on the internet use square brackets. And you should not use square brackets on this class. Okay? Square brackets are faster than dot at, but this class, you should not be concerned with speed. You should be concerned with not being bad, coding-wise. Okay? So what does this do? This will access whatever's in memory there. What do you think it's going to do? What number do you think is going to get printed? Or do you think it's going to crash? Put some money down on this. Crash, random number. Let's find out. Seg fault, core dumped. But not a good, it's not a good crash. Like, this is actually the thing, like, it bounce checking, and it detected it, and it crashed, and it said this is what happened. This is just your program, like, blowing up. This is the bad kind of crash. This is the good kind of crash. Okay. And that's actually good, because if it crashes, at least you know you screwed up. Now let me show you the scarier thing, which is it doesn't crash and it just gives you a random number. Why did that give me a random number? Why did that not give me 0? I thought you said, Professor, that vectors initialize all 10 of their elements to 0, and I'm accessing element 10. Why did it not print out 0? If you have 10 elements, they range from 0 to what? This is something that a lot of students were confused by with the input tester. They're like, are there only 9 input tests? I'm like, no, there's 10. But it only goes up to 9. Yeah, because there's a 0, right? 0 to 9 is 10. And so this is out of bounds. And it's not out of bounds far enough for it to actually crash the program. If I went far enough out of bounds, it'll crash, all right? But if you just go a little bit out of bounds, it doesn't crash. That's terrifying. This is actually really, really bad. It's actually good for your program to crash because then you can trace it back and find out what you did wrong. It would actually be even worse if it was just printing 0, because you're like, oh, look, I tested it, it worked fine. This is why you should never use square brackets in this class, okay? Because that code is bad. It's out of bounds. This should not happen. Like, it should not run. You should immediately be told, no, you went out of bounds. And it doesn't. Square brackets will just very happily and silently fail. Or succeed, actually, depending on your perspective. And so if you want to have some fun, you can, like, print out the contents of memory. Like, for I equals 0, I is less than 100, I plus plus, see out vector 3, square bracket I. Let's do vector 2, actually. Vector 2's got some numbers in it, right? So this code is going to print out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then it's going to print out just whatever's in memory there. Okay? This is why square brackets are bad. Run, type through more. Okay, so here we go. The first 10 elements are all there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The next element is 49. Then we got a bunch of zeros. Then in RAM, we got 858, the San Diego area code. We got that. We got that. Then a bunch of zeros. I don't know. Do you understand? Like, we were just printing out what's in RAM. This is bad. Like, are you with me on this? Like, no, don't do this. Yeah, you'll make me sad if I see square brackets this semester. Yep. You'll see lots of people online. You'll see Zybooks using square brackets. You'll see people online using square brackets. I was showing people in the 12 o'clock class how to use GitHub a little bit. GitHub is a code repository. Well, Git is called a source control system, and it allows people working on the same project to share source code with each other and things like that. And so I showed people how to, like, come to here and search for, like, Battleship. And, like, if you wanted to, like, download some source code to do Battleship, you could search for Battleship and click on C++. And that's Qt. Eeks. It's a Berkeley. Somebody at Berkeley made Battleship. All right, let's check that one out. So here's their Berkeley Eeks class Battleship. So I click on this hyperlink here, and so I could look at all their source code files here, right? I could take a look at all their stuff on the website, but generally speaking, what I'm going to do if I use GitHub, and this is industry standard. This is something that you're going to see. You're going to need to know. Git Clone, and I clone their Git repo, and then if I cd into that directory, I now have a copy of all of those files on there. Yay, cool. And let's see if there is a make file. There is. I'm going to type make. And so it compiles their code, and I can run it. It's called Battleship. There's Battleship. It's time for Battleship. I would like 3 battleships. D4. All right. E5. F6. G7. Oh, the row. Okay. Number for the row. Okay. 1. Column A. Okay. Dresden row. Okay. There we go. All right. Sit down. So they're probably using some sort of vector, or if they're bad, they're probably using an array. And let's see if we can figure out what they're using for. .h. And they are using an array. So they're bad. Okay. As expected. Berkeley loves writing old obsolete code. I don't know why, but they do. They love themselves some pointers and arrays and things like that. I can't give you any good reasons why they should, but they do. Yeah. Pretty standard object-oriented. There. Executive.cpp. Time for Battleship. Let's see if they game start. Somewhere in here, they're going to have like a 2D array. -rf eats. I think I downloaded another one. There. So yeah, you should not be doing what they're doing. You should be using vectors instead. And you saw, like, well, if you had looked at their code, you'd see they have square brackets probably everywhere in it. And that's just not, it's not good. Now, those people might say, well, just don't write bugs. Just don't write bugs and you won't have any problems. Because square brackets is faster than .at. To which I would say, yeah, everyone writes bugs. You know, and how fast do you need Battleship? You know, you're doing like one board lookup every 10 seconds. Your CPU runs at 4 gigahertz. Use .at. Okay, it's just better. And if you really need the speed, I give you permission to switch out the .at with a square bracket. If you really need the speed, I give you permission. But I guarantee you that for your 4th year Battleship assignment, you do not need the speed of square brackets. Square brackets is fast and unsafe. .at is slow and safe. And it's not really that slow. So, okay. Rant off. When is it appropriate to use square brackets? Yeah, when you need speed. Like if you're doing something in, you might even like run your code first with .at to make sure that you're not going out of bounds, and then replace it with square brackets when it's in a hot loop that runs millions of times a second. Sure, you know, knock yourself out. Okay. So you see what happens if we use .at when we tried accessing that memory past the boundary. It crashes, and in a good way. It's a good crash, and it tells us, you know, you tried accessing element 10, the size of the thing is 10, and so you're bad. Because when you have size 10, the last element is 9. Right? So it literally tells you what went wrong. Okay, and that's why .at is thumbs up and square brackets is thumb down. Now, if you use address sanitizer, you could probably make a case for square brackets, but, you know, another story. Okay, but yeah, you will see lots of people online using square brackets. It's just a bad idea, in my opinion, because, like I said, you can read to it, you can write to it. That might not be your memory. You might be reading and writing to your credit card number or to your phone number. And it works because you wrote to it and you read from it later. It's the same value there. But then, like 5 hours later, when you try printing out your phone number is, you know, your Battleship score. You're like, what? How did my number become? I never changed my number. How did my number change? It's my Battleship score. And then it just becomes this impossible to debug situation. So take it from me that has had to deal with a lot of memory bugs over the years. Just use .at for everything until you decide that you need the speed. And a lot of times you'd be surprised that you don't. Okay. So let's come back to here. Make 0 runs. So this seems worthless, right? So this is actually my most common way of making a vector. It looks like, but it's pointless. Like there's no point to having no elements in a vector. So why would you make a vector with no elements? And that's because vectors can grow. Vectors aren't just fixed size like arrays are, if you know what an array is, which I barely even teach in this class because vectors are 9,000 times better. At Microsoft, Malia said there's two data structures they use. One is vectors, which are used all the time, and the other one is hash tables. And you'll learn hash tables maybe in this class, maybe in CSI 41. But those two data structures are basically 90% of everything you need. So a vector of size 0. So how do we grow it? Okay. So vector3 dot push back increases the size of the vector by 1 and adds 10 to the end of it. Okay. Okay. So let me sketch out what's happening here. If I want to print the thing, I could do the for loop like I showed you before, or I could use a range-based for loop, right? This works the same way. For every integer in vector3, thank you. See out the integer. Voila. This is going to print all of the elements in vector3. And it's going to print 10, 20, 30, 40, 50. Okay, so what's going on here? Let me draw it for you graphically. All right. A vector is like an accordion, sure. Okay. So it's like a string actually. Well, strings are vectors. Okay, so let me show it to you. So when you start off, you have vector3 here, and it's empty. So you got like some memory address where the thing begins, and it's like just kind of like empty. And you call pushback 10, and 10 goes in there, and now it's got one element. You call pushback 20, the vector grows to size 2. It actually allocates a little bit more memory. How that works is a topic for another time. It's actually pre-allocated most of the time, and occasionally does a full reallocation. It doesn't really matter for our purposes right now. We call pushback 30. The vector is now size 3. Pushback 40, it allocates another chunk of memory, puts a 40 in there. Pushback 50, it allocates another chunk of memory, puts a 50 in there. Okay. And so this is this is vector.at0. This is .at1, index 2, index 3, and index 4. Okay. And then when we do a for each loop, when we say for each x in the vector, we do a for each loop like this. We're saying for every element of the vector, for each int we call x in the vector, see it out. So we're first going to print out 10, then we're going to print out 20, then we're going to print out 30, then 40, then 50. So first time through the loop, x is 10. So second time through the loop, x is 20, 30, 40, 50. Okay. And this is different from when we do the standard for loop where I is the index. So x is the values. If we were to print it out the standard way, for size bi equals 0, I is less than vector 3 dot size I plus plus. So when you do a regular for loop, I is the index or location of the data. X is the value of the data. So these two for loops do exactly the same thing. Vector3.I. These two for loops do exactly the same thing, but I in the first place is the index, which is 0, 1, 2, 3, 4. Do you guys see that? It's this number. This is I. I is that number there. Okay, it's the index. Whereas when you do a ranged for, when you say int x in vec3, x is the actual data value. You guys understand? They do the same thing, but the ints are a little different. In one case, it's the location of the data. The other is it's the actual data. Okay. So these two loops here are exactly the same, but you know the ints mean something a little different. Okay. So this is saying, give me the value at location 0, give me the value at location 1, give me the value at location 2. And this one is just print the value. Okay. So I personally would prefer using a range base 4. In situations like this, it is less typing, it's less error prone, it's the same speed. So that's my advice to you. Now, one final learning point for today, and that is how to pass a vector to a function. So let's say I wanted to make a print vec function. So I print vec, taking in a vector of integers named vec. So rather than doing all this stuff here, just go with the regular for loop. Then we can print vec1, vec2, vec3. Do you guys see that? So we are passing a vector of integers to this function here, and it's going to print vector 1 first, which is going to be 100 zeros. Maybe I should shrink that a little bit. Let's do 10 zeros. So 10 zeros, then it's going to print out 1 through 10 for vector 2, then it's going to print out 10 through 50 for vector 3. Does this make sense? But we've got an issue right here. So before we talk about the issue, does this function make sense? All this code works, but there's something kind of wrong with it. I mean, it's not wrong from a correctness standpoint, but it's wrong from an efficiency standpoint. So we're passing a vector to a function, and then we're saying for every element in that function, print it out. Or for every element in that vector, print it out. And so then we don't need to write that loop every time. We just print back and pass it a vector, and it gets printed to the screen, and everything's great. Okay. So the efficiency thing is here, okay? Is this parameter here being passed call by value or call by reference? Do we put the couts in the function? Yeah, you can have couts in a function. The reason why I've been telling you not to put couts into a function is because a lot of students get confused about the difference between returning a value and printing a value, okay? Printing a value goes to the screen. It doesn't have any interaction with the code whatsoever. So like if I was making a square root function, square root bill, and I like did this, cout the square root of f, this is like ultra bad. Okay, and a lot of students write code this way. They're like, but I'm printing it to the screen. Yeah, but you're not returning the value. Like you promised that you would return a double, and you have no return statement anywhere in your code. Like if you remember from the beginning of the class, that could cause your code to segfault, right? And so there's a big, big difference between printing something to the screen and actually returning something back into main. What we need here is to return the square root of f, not to print it to the screen. And so like I tell a lot of students, just don't put couts into your functions, just so that they don't get into that habit of like confusing writing something to the terminal versus something in the code itself passing a value back into main, like an algebraic function. Okay, but there's nothing wrong with couting something. In fact, this function is called print vec. I would expect it to print things to the screen. That's fine. Okay. So this is not call by reference. This is call by value. Okay, and so call by value makes a duplicate of vec. Okay. Now, making a like if you pass an integer by value, it's not a big deal, right? You're duplicating an integer. Who cares, right? But what if our vector has like 1 billion elements in it? Do you guys see what the problem is here? Like imagine the vector has 1 billion elements in it. If we have our code right here, what it will do is duplicate all 1 billion elements, then it'll print it out, then it will throw the duplicate away. Is that good or bad from an efficiency standpoint? Yeah, it's very inefficient. Yeah, it's bad, right? It's very, very good. Very bad. I mean, very good that you got, it's very bad. Yes. Good. No good. Yes. Good. No. Yeah. You know what I mean. Okay. Anyway. Moving on. So the correct way of doing it is you pretty much never want to dupe a vector. Ever. Like, vectors are almost never called by value. The only time I'd ever call a vector by value is if I deliberately wanted to duplicate it for some reason. Yeah, it just basically never happens. I mean, I'm sure I could contrive an example, but this is really bad, okay? From an efficiency standpoint. Call by reference passes the original vec in instead. So if we change the code just to this, now what happens is when you print it, the original vector comes in instead, and then it just prints all the elements in the original vector, then it goes back. No duplication, no creation, no destruction, much, much, much faster. But this means our vec can be changed, right? And most of you, when you're learning call by reference, you think of call by reference as meaning I want to change the value passed in, right? Like we did the doubler function last time, right? You pass x to it, and x gets doubled, right? It would be really weird if our print function changed it. You know what I mean? Like if I just slapped into here like vector.at0 is equal to 666, right? This would be very strange behavior. But this is valid code. Do you get what I'm getting at? Like if I call a print function, I'm not expecting the print function to modify my vector that I'm printing, right? That would be very odd, right? You guys get what I'm saying here? Like if I'm I'm not the person who wrote printVec. I just am like, oh, there's a printVec function. It just prints my vector. You get what I'm saying here? Like it's just very odd. Like, yeah, I'm just gonna set every element in 0. Yeah. And you can do that with a range-based for loop. If you want to modify something inside of a range-based for loop, you have to do call by reference here as well. And so this is going to print all the elements in the vector and then wipe it all out. And this is very probably not what I would expect from a print function. You can print the vector once and then it's dead, right? So how do you prevent that? Because call by reference is what we want, right? Call by reference is what we want. We don't want to duplicate the vector, but we also don't want it to change. And so let me show you the pro tip, number 3 for the day. Vectors are 95% of the time passed by const reference. Okay, so what does that mean? It means this. So if you pass something by const reference and then you try changing elements in it, it won't work. It won't allow it. Okay. So this is what you do 99% of the time. When you're passing a vector to a function, it's almost always const, then vector of integers or whatever kind of vector it is, vector of integers by reference. Okay? So you have a const in front, you have a reference after, you can name it vec or vecnar or whatever you want, doesn't matter. And that will prevent all instances like that of trying to change the vector. This is the pro tip. This is the God tier way of coding with vectors. If you're going to pass a vector to a function, you almost always pass it const reference. Okay. So you can print it, but you can't change it. You can read from it, you can't write to it. You don't make a copy either. It's not call by value. Call by value duplicates it. It's not call by value. It's call by reference, but you can't change it. So if I ever see something that's call by reference that's not const, I'm assuming you want to change it. That's how prevalent this is. By default, all vectors are going to get passed by const reference. It's only if I don't see a const do I assume you are going to change it. Okay. And you can pass in non-const vectors. Like you see how this is all working here. This guy is not const. He's not a constant, but I can still pass it in. And he just becomes protected for the time he spends within the print vec. So when you pass vector 1 here, he can't change inside of here, but then when you go back out, he can change again. So it just says while you're within this block of code, you're immutable, you're untouchable, you're given the aegis, you cannot be touched while you're within this function. Okay. What do you guys think? That makes sense? Do you understand the rule? And the only time I'm not going to make it const is if I'm going to do something like set everything in the vector to 0, right? So if I want to make a function called like void 0vec, which is going to just set everything to 0. Then obviously it's not going to be const reference. Okay. So if I'm actually modifying the vector, sure. Okay. 0vec, or I can make a function that randomly generates numbers or something like that, sure. Not const reference. But most of the time, the great majority of the time, you're going to pass vectors as constant reference. Okay. So that should help you with your Zybooks. One of the Zybooks questions involves like a vector of bools, I think. I'm probably going to move that one to next week's homework assignment because we didn't cover it till today. So I'm going to take that one out of the current week's assignment. I'm going to put it into the next week's assignment. And next week's assignment will be on vectors. So yeah, get cracking on it, and then work on Mandarin, and we'll probably talk a little bit about Mandarin on Wednesday, but start it now, try and get it all done now, so you can have questions for me on Wednesday. And that's it for today. Hope you guys liked vectors. They're very useful stuff. The most common way, actually, I work with them is this. While true, out, please enter a number, 0 to quit, x equals 0, send to x, if x is equal to 0, break, vec3 dot push at x. This pattern here is exceptionally common, okay? This code pattern here is exceptionally common. You will see this cropping up everywhere. Where basically you don't know in advance how many things you're going to read, right? You're reading it from a file. You don't know how many things are in the file. You're having the user type in their tax receipts. You don't know how many tax receipts they have, right? So what you do is you just keep entering more and more data. And every time the user types in something, you check to see if they're done. If they entered whatever magic number means they're done. If they're not, you add it to the vector and repeat. And so that will sit there and just grow the vector. They keep typing in numbers. All those numbers get saved into the vector. Okay? And so if we run this code, and then I really will be done for the day, I promise. 10, 20, negative 30, negative 40, 50, 60, negative 70, 80, 90, negative 100. And you'll see here in vector 3, we got 10, 20, negative 30, negative 40, 50, 60, negative 70, negative 80, negative 100. Okay, simple as that. Okay, this pattern here is extremely, extremely useful and extremely common, where you just sit there and keep reading in things and add it to the vector. So this kind of stuff is like, it's not very good, right? Because most of the time you don't know how many, how many things, like how many people are you going to invite to the wedding? Like you don't know in advance. Like you're just going to sit there and enter names. Like you don't need to know in advance. And so usually I don't make vectors that have a fixed size or with fixed values and things like that. Like it happens. Like it's a tool in my tool belt. I've certainly written code professionally with both these things, but just my most common way of doing it is just to make a vector of size 0, and then I read from a file, and I just keep reading numbers from a file until I hit the end, and then my vector is filled with all the data from the file, and then phase 1's done. Phase 1 is usually read data. Phase 2 is computation. Phase 3 is usually output data. That's kind of the standard pattern for most classical computer science programs, right? Data entry, data computation, data output. Not talking about games and things like that, but like traditional old school computer programs, that's the essence of computer science, according to some professors. Input phase, computation phase, output phase. And this is how you can do input. No fuss, no muss. It's real easy. So we'll give you lab time to work on this on Wednesday. But I'm done. I'm done now. I promise. All right. I'll see you guys next time. Peace.